Hi again. In the last two tutorial segments, we used the multi-camera array microscope, the MCAM, to acquire a vibration startle response video of 96 zebrafish in a 96 well plate, and then we looked at the machine learning tracking analysis of this data and the associated options and data outputs of this workflow. In this tutorial I'm going to show you how to acquire a different type of assay called the visual motor response, or VMR. The VMR is a popular assay that implements alternating phases of visible spectrum illumination and darkness. During the transition from light to dark phases, the zebrafish are startled and their distance traveled, or the number of fish that respond to the stimulus, can be quantified as experimental endpoints. In the vibration startle assay, we looked at how to acquire a video with vibration stimuli and all of the associated options. In this assay, we will skip over the discussion of the majority of the assay options and just focus on those important to the VMR assay. Also notably, because the duration of light phases in this assay can be significantly longer, we do not want to record all of the time between phases that we will not analyze, so we can acquire this recording as a video time-lapse. This will help us decrease the data size we are saving and the processing time required to analyze the data. It may be a good idea to review the vibration startle tutorial before working through this example. So far I have opened the MCAM acquisition interface and clicked Stream All Sensors at the top of the screen to see what is happening in our well plate. For this assay, the infrared filter has been installed in the system because we will be using changes in visible light and we would like consistent lighting to reach the camera sensors throughout the experiment. Additionally, I have already optimized the imaging parameters and focus level for behavioral assays described previously. To begin with this assay, open the Stimulus Assay Time-Lapse panel from the Assays menu, go to the Zebrafish tab, and then select Acquire Stimulus Time-Lapse. Again, as with the vibration assay, we will select a well alignment file. We have full array acquisition selected. We have high frame rate selected in the top left corner. For this assay, we will acquire at 30 frames per second for 1 minute. Also for this assay, we will enter a background intensity lux value of 1500 lux so that the visible spectrum light is on for the duration of the experiment. Instead of creating light flashes, we will insert periods of darkness in the overall light period. Add the dark phase by setting the flash stimulus at 30 seconds, for a duration of 30 seconds, with a lux value of 0, and click Add Stimulus to add it to the protocol. Next, select a file location, remembering we want to save to somewhere on the MCAM data drive. And enter a file name for the acquisition. The final parameters on this panel will control how the assay phase we have set up is repeated as a time-lapse. Here we will set a start delay of 2.5 minutes, for iterations, and a period of 210 seconds. Finally, I will start the acquisition by clicking Acquire Time-Lapse, and we can see the initial delay timer begin. As this acquisition progresses, let's briefly discuss a few aspects of this assay. First, notice the setup of this panel where we have the assay phase definition in the center of the panel. This section mirrors the assay panel that we saw in the vibration startle previously. Then at the bottom we have the settings to control how we iterate this phase. Also at the top are the options to save and load the assay protocol, which we discussed previously. Next, notice the specific timings of this assay and how they work together. First, we have a start delay of 2.5 minutes, followed by a 1-minute recording where 30 seconds is light and 30 seconds is dark, so overall we have 3.5 minutes with 3 minutes of light and 30 seconds of dark. With a 210-second period, we have taken up the first 60 seconds with our initial recording, leaving the next 150 seconds, or 2.5 minutes as the next light phase delay. When we repeat this 4 times, this is the overall layout of light and dark phases. Overall, we have a total assay duration of 16.5 minutes with 4 1-minute video acquisitions distributed throughout this time period. Once the acquisition has completed, we can proceed to analyzing the data. In the next tutorial, we will take a look at analyzing this data through a batch analysis. Again, this assay is designed to be flexible and many aspects can be customized to your experimental protocol. If you cannot figure out how to modify this workflow for your needs, please contact us at help@ramonaoptics.com. Thanks for following along.